Okay, this is episode 8 of the energetic series. This is going to be advanced explosive design. This is a academic class, so it's going to be pretty dry compared to the other ones. But it's going to be a ton of data. I'm not going to be fielding questions in the comments for this episode simply because there's going to be too many. You shouldn't have any issues with understanding the information, although the kind of the higher echelon of what's going on is complex. We're going to break it down into a field serviceable skill that you can use in advanced demolitions. This is way beyond, this isn't in like an 18 Charlie program for the military. This isn't, there's some pyrotechnicians that use this. There's some explosive engineers that use this professionally, but very few people are even aware of this method, and it's fairly new. The method comes from Jain, that would be Jain. That's an Indian out of Bangalore, India. So he had a PEP article in 1987, Interjects of Propellants, Fuels, and Explosives, a Chemical Valence Approach is what the paper is called. It's a pretty smart theory and technique that works really well. The paper itself, it's behind a paywall, but if you do find it, it's kind of a little bit inaccessible for the layman. There are some subsystems that people have developed using this theory to analyze compositions. One that's really accessible is CONKLING. He does Chemistry of Pyrotechnics. It's a recurring series that he wrote. He's deceased now, so he's no longer with us, but he did this for a long time. And the method came out in 1987. So you have to find it in CONKLING, you have to go to later editions because it doesn't even get picked up until later. So out of this system, essentially, to break it down, the really big picture, we are assigning an electron imbalance to reactants to then balance in-state electrons in a chemical reaction. That's what's going on. So it means that we are connecting a valence number to a molar unit. So once you understand that, then you can understand how you can move around mathematically in here in terms of conversions and things like that. So I've got my own system that is very simplified. I find that people have a lot of trouble with algebra. In teaching this, I break it down to do multiplication and division. The most complex part of it is perhaps maybe like a simple cross multiplication, where you're taking two fractions of comparable units and then you're cross multiplying to find an unknown variable. So what does this system do? Why is it important? Well, it's going to give you a really thorough understanding, technical understanding of redox in explosives. So every reaction, all your common pyrotechnic and explosive reactions are simply redox reactions. That means that you have electrons that are exchanging between species. So the thing that's giving up an electron is said to be oxidized. The thing that's going to be gaining an electron is considered to be reduced. It's not terribly critically important that you understand that or comprehend it, but just know that that's what's going on in a redox reaction. For all of history, from black powder up until even composition C4, things like that, the way that they're designing, the engineers, explosive engineers or ordnance corps are designing explosive is typically trial and error, so it's very costly in time and man hours, and generally they're designing compositions based on the physical properties, so sensitivity and handling properties and packability, things like that, to be able to use an explosive. That's typically what goes into that's the guiding principle for designing explosives in the past. So contrasting that with a modern pyrovalent system, it gives you the ability to competently balance your reducing and oxidizing species to achieve theoretical maximum energy output in a detonation. But this goes even further than that because modern developments in explosives and munitions, you have concepts like thermobaric explosive, enhanced blast explosive. They're pretty confusing to people that are trying to understand what's going on, and understanding electron theory and redox theory helps to define and understand what something like a TBX or EBX is. So if we balance everything in terms of the electrons, then we're going to get maximum energy output, right? If we are adding oxidizer into a composition, in order to do that, that is what is known as enhanced blast explosive. So you're providing additional oxidizers to maximize explosive output, maximum peak pressure, maximum heat that's available from that detonation. If you add excess fuel to an explosive composition, depending on how it's done, you can cause the fuel to be catalyzed through detonation to react with oxygen in atmospheric air. And the result of this is that you're going to get a dramatically increased explosive pressure window for duration. So your high pressures are going to last a lot longer. They're going to extend out to a greater radius, so it increases the range of weapons. What you give up for this is that your peak pressure, your maximum peak pressure, is going to reduce. The peak pressure is so, comparably brief to how your sustained pressure will behave that there are a lot of situations where that is more desirable. Thermobaric explosives are really effective at destroying structures, pushing down walls, blowing things apart. They're great at that. They're good at killing people, and the reason why is because if you're within range of a thermobaric explosive, you're getting increased pressure. So around 200 psi, the body is you're going to die. That's known as a primary blast injury. So a primary blast effect is when you're you typically go through cardiopulmonary hemorrhaging, where you're leaking, you're going to start leaking out of the lungs, and it's not recoverable. And that's what you'll find at blast sites. When you find a blast site with casualties and they're going to be on the ground, typically deceased, leaking a lot of fluid, and that's because they have undergone death from a primary blast effect. Secondary blast effect is like things like shrapnel, getting limbs blown off, stuff like that. That's what people generally think about when they're thinking about explosive effect, but the actual explosive effect is heat and pressure. So just to give you an example of this, back in the Carnicon days, I have an episode called LMGs, where I shoot a bunch of light machine guns, and at the end, I shoot a 40 millimeter grenade at cocaine, and the cocaine detonates, right? Well, what that actually is in the video is about, 2 pounds of ammonium nitrate sensitized as tannerite mix, and then it's probably got somewhere between 20 to 40 pounds of powdered confectionery sugar, like icing sugar, very fine sugar, tightly compacted in bundles on top of the ammonium nitrate tannerite. It'll create pressure waves on the ground. It'll throw stuff and break stuff apart, blow stuff apart. So this is an example of a low order dust initiation explosive, which is a type of thermobaric explosive. Okay, so let's get into explosive design by first understanding this valence approach. Basically, any composition that you're going to make is going to typically include, you could use this in compositions where it's all fuel, and then you're going to have a fuel-rich composition. You could use this to analyze it and see just how fuel-rich it is. The actual purpose here is to achieve maximum energy output. So the way that you do that is you take whatever material is your explosive, TNT, HMX, RDX, whatever. So that's your explosive. Then the idea here is that you're going to introduce an oxidizer with it in order to balance that reduction potential of the fuel. So how we do that is when you have an explosive redox reaction, the products are known. Because the conditions are so high pressure, generally you're going to have very predictable products. There's a lot of them. I'll show you a table here. So what you do is you take that end state, what it's going to be, what it's going to end up as, and you assign it to whatever the precursor element is that is going to turn into that end state product. There's a lot of elements that can be used in explosives, but 90% of the time it's going to be CHNO. Carbon, hydrogen, nitrogen, and oxygen. That's what you're typically going to see. What you want to remember is that carbon, it's always going to go to CO2. The valence of CO2 is +4. Hydrogen is the next one. Hydrogen goes to H2O, that's water. That would be a +1. In nitrogen, that's going to go to dinitrogen, that's N2. So that's that's the gaseous nitrogen. That's what it goes to. And you're gonna love nitrogen because when you're doing these calculations, every time that you see an N, you can just think, skip it, 0. O is oxygen. That's gonna go to H2O. In other cases, you'll have oxides. So like if metal's involved, you're gonna have metal oxide as a product. So that's gonna be -2 at the valence state. Chlorine, you'll get hydrogen chloride, HCl. You can also get chlorides, and that is assigned -1. Fluorine is going to go to HF for fluorides, also -1. So these are halogens. They oxidize like oxygen. They're just not as effective as oxygen. So O, oxygen, was -2. Chlorine and fluorine are -1. Aluminum, as an example, because that's a common fuel that gets used in explosive, like aluminized explosives. That'll go to aluminum oxide, that is +3 valence state. If you commit that to memory, it's going to make this whole process a lot easier. Okay, so the next step, you now understand how to account for the assigned valences of each of the elements that are going to be, in a material that you want to introduce into an explosive composition. You sum all the valences, so your negatives and your positives, whatever your result of the sum is, it's either going to be positive or negative. If it's positive, that means the material you're dealing with is a net fuel. If it's negative, that's a net oxidizer. Fuels with oxygen will typically produce less heat output in the reaction than something that's just straight carbon hydrogen. Something like a simple sugar. So sugar is C6H12O6. Well, it's got a net valence of 6 carbons at +4, 12 hydrogens at +1, and 6 oxygens at -2. So if you sum all that together, you should get +24. So +24, it's positive, it's 24, so that's quite, 24 is up there. So this is a net fuel, it's quite a fuel. Even though the sugar contains 6 oxygen. It doesn't matter because they're all going to be used up. It's not usable oxygen in the detonation, right? So then let's take an explosive fuel, something that's typical, so like TNT, for instance, C7H5N3O6, right? So this is a CH&O explosive. This is what you're going to commonly find with explosives. Pyrovalence calculation there, you're going to have 7 carbons, those are at +4, so 7 times 4. 5 hydrogens at +1, 3 nitrogens at 0. Remember what I said about nitrogen, you can skip it, right? Because you're 3 times 0, nothing, right? So just skip over nitrogen. 6 oxygen at -2. The net valence of the molecule, TNT, is +21, so it's a fuel. All right, moving on to something interesting. A nitramine explosive, so it could be either, in this case, we could be talking about RDX or HMX. The difference between these molecularly, HMX is a set of 8, so you got H8, N8, O8, it's a C4 for carbon. And then RDX is going to be 6. And by 6, what I'm saying is it's a set of 6 with less carbon because it doesn't have much carbon in the body, right? So out of your valences, your total number of fuel valences in HMX, C4, H8, N8, O8, you've got a total fuel valence of +24. And then in terms of the oxygen, which would be your oxidizer valences, -16. So this is a net +8, meaning that HMX is fuel rich. But what's interesting about these nitramine explosives, particularly HMX and RDX, is that for both of these, +8 is what you get when you're sending your carbon to CO2. But if you send carbon to carbon monoxide, then you're going to get 0. You're getting a 0 valence because for carbon monoxide, anytime that you would only use the carbon monoxide valence if you are sure that more of the carbon goes to carbon monoxide. And the only way that you would know that is if you were able to analyze the detonation products, which most people aren't going to be able to do. So that's something that's left to professional scientific literature. Any pyrovalence calculation that you're doing for RDX or HMX, you will send the carbon to carbon monoxide. Carbon monoxide is +2 instead of +4. So carbon dioxide is +4, carbon monoxide is +2. So when you do HMX, you're going to have fuel valences of +16, and minus 16 for your oxidizer valences. So this is a net balance of 0, which accounts for the extreme detonation performance of both HMX and RDX. So as you begin to build your repertoire of valence calculations for different materials, what will happen is you'll just develop a list naturally. You should have a list of anything that you would use that's an oxidizer, anything that you would use that's a fuel or an explosive. Most explosives are fuels. This is why ETN is really unique, because it's an oxidizer explosive. There's not a whole lot of them. They're pretty rare. Ethylene glycol dinitrate, that's a neutral explosive. It's 0 in terms of its valence state. But ETN itself is a net oxidizer, so it's very unique. And this is what spurred this video, is because we're going into the use case of ETN, and we just can't really do it in good faith without covering the system of how to make composition. Okay, so what we've done so far is learn that we take a material that we want to introduce into a composition. We're going to sum together all the elements, their in-valence states of what their products are going to be. The sum of that is either going to be positive or negative. If it's positive, it's a fuel. If it's negative, it's going to be an oxidizer. So for example, if we take a material like an oxidizer, ammonium perchlorate, very common oxidizer, it's got an in-valence state -5, right? So once you know the valence states of all the reactants that are going into an explosive composition, now you can input your products and balance the equation based off of the valence states. So it's actually a really cool and simple, straightforward procedure. What's going to happen in the end, in terms of when you balance this out, it's going to be a net valence state of 0. So you're on the left side of the balanced equation, you're going to have a certain number of CHNO or whatever other elements are in the material. On the right side of the equation, you're going to have an equal number of all the elements. So they're going to be the same on both sides. Altogether, it's going to be a net valence of 0, and that is a balanced equation. Matter is not created nor destroyed. If you have trouble in balancing, 99% of the time it's going to be because your valence is messed up. Like you inputted the wrong valence. If you use the wrong valence, it's going to completely throw off your balanced equation, and you're not going to be able to get the same number of products as the same number of reactants that go into those products. They're going to be offset. You're going to have odd numbers. You should always suspect that, oh, I messed up my assigning my valence, and you double check your valences of your reactants. Okay, so with that, let's talk about balancing equations. For this example, this is straight out of CONKLING, but it's a great example, so we'll use it. Balance glucose and ammonium perchlorate. You have to remember the oxidizing valences will equal the reducing valences, and the sum of the valences is going to be 0, right? And this is a great example because we've already discussed ammonium perchlorate. We already know it has a valence state of -5. So for ammonium perchlorate and glucose, so ammonium perchlorate is NH4ClO4. Glucose is C6H12O6. So ammonium perchlorate is a valence state of a pyrovalence of -5. Glucose is a pyrovalence of +24. +24 is a fuel, -5 is an oxidizer. What we do in order to balance it, the first step, and this is very simple, just don't get wrapped around the axle, just do what I say, okay? So you take, you're gonna switch around the valence states. So what you do is you take that, ammonium perchlorate has the -5, okay, that's the oxidizer. Glucose has the +24. So you're gonna take that 24 of the fuel, and you're just gonna throw it onto the ammonium perchlorate, okay? Then you're gonna take the -5, you're just gonna, disregard the minus part, put 5 for glucose, right? And so this is going to set you up to have a correctly balanced equation. It's kind of like a cheat shortcut using the power of valences. So what that's gonna look like is, you're going to have 24 ammonium perchlorates and 5 glucose. And the reason why it's the number 24 and 5 is because ammonium perchlorate, originally when you did your valence calculation for it, what its pyrovalence is, you got -5.
and for glucose you got plus 24. And between those two, there is no lower factor. You can't factor out 5 and 24. That's the minimum that you can go. If, let's say, ammonium perchlorate was -6, well, then you could factor 6 and 24. 6 and 24 factor would be 1 and 4, right? But you can't do that because it's not 6, it's -5, right? So -5 and plus 24, there are no lower factors. Therefore, the numbers that you're going to use are 5 and 24. You switch them around. You're going to put 24 and assign it to the oxidizer, ammonium perchlorate. You're going to take the -5 is going to turn it into a 5 for your glucose. And this is going to set you up for a totally balanced reaction. After that, we're going to get our detonation products. So this is what's going to finish the balanced reaction. So I already told you CHNO is what you really need to remember. The products for that are always going to be the same. So what I do is I go write down each element and total them, right? I add them up and total them. So nitrogen is first in NH4ClO4. So nitrogen, you've got 24, right? Because you've got 24 ammonium perchlorates. So right away, you've got 24 nitrogens. There was no nitrogen in the glucose. There was only nitrogen in the ammonium perchlorate, right? Out of the ammonium part of the ammonium perchlorate. So 24 was the total because I had 24 ammonium perchlorates and I had no nitrogen in the glucose. If for some reason you're trying to balance an equation and your nitrogens aren't even, like if you had 25, something like that, you messed up your valence. So you go back and check your valences. Okay, and then following left to right, the next one is going to be H because the first molecule here is ammonium perchlorate, NH4, ClO4. So the H is after the nitrogen. So I've got 24 of them because I've got 24 ammonium perchlorates. 24 times 4, that equals 96. Then I'm going to annotate next to that. I'm going to add to that, I'm going to go into the glucose and look at their hydrogens. So glucose has 12 hydrogens, but in terms of the equation here, I've got 5 total glucose, right? So that means I've got to do 5 times 12 to get the total number of hydrogens. That's going to be 60. So now I have to add the hydrogens from the glucose and from the ammonium perchlorate. That's going to come to a total of 156 hydrogens out of both these materials. Now let's continue moving on down the ammonium perchlorate molecule that I've written out here, NH4ClO4. We already did N, we just did H. Now we're going to go to Cl, that's the chlorine, right? So chlorine, I've got 24, right? There's no other chlorines in here. There's no chlorine in the glucose, right? There's only chlorine in the ammonium perchlorate. So I've got 24 ammonium perchlorates. That means I've got 24 chlorines. Now let's move on to oxygen. So for oxygen in ammonium perchlorate, I've got NH4ClO4. That means I've got 4 oxygens for each ammonium perchlorate. I've got 24 ammonium perchlorates. So that means 24 times 4, 96 oxygens in ammonium perchlorate. Then we're going to go on to the glucose. We've got C6H12O6. So you've got 6 oxygens out of the glucose. You've got 5 total glucose, right? So that means you're doing 5 times 6 is 30. So now you're going to add your total oxygens from your ammonium perchlorate and your total oxygens from your glucose. That's going to be the 96 plus 30, and that's going to give you a total of 126. So you have 126 oxygens. Lastly, we're going to go into carbon. The reason that we're going into carbon as the last element is because that is the last element that is written out here on the left side of the equation. We have what we've written is 24 NH4ClO4 plus 5 C6H12O6. So we've already gone through nitrogen, we've already gone through hydrogen, we've already gone through chlorine, we've already gone through oxygen. The only thing that's left is carbon. No carbon at all in ammonium perchlorate. That's what's known, anytime you have a molecule that doesn't have carbon, that's known as inorganic. Sugar is organic, it's got carbon in it. So we skip the ammonium perchlorate, we're going to go into the glucose here. Carbon, you're going to have, it's C6H12O6. So that means we've got 6 carbon and we've got 5 of them, right? Because we've got 5 glucose molecules reacting with the 24 ammonium perchlorates. So that means the total 5 times 6 has 30, right? So we've got 30 carbons. So what we have total, let's just recap here. 24 nitrogen, 156 hydrogen, 24 chlorines, 126 oxygen, and we have 30 carbons. So now when I'm writing out my product side, we're going to take this total list of elements that we've already summed up here, and we're going to apply it in a known product. So we know right away, we're going to do all the easy ones first, and then we'll do the ones that could be a couple of different ones and talk about how to figure that out. So the first right off the bat, nitrogen, super easy, right? So nitrogen is always a 0 in pyrovalence calculations, so it's great. It's also great in terms of figuring out your detonation products, because nitrogen always goes to N2, right? You're going to go to dinitrogen. So 24 nitrogen totals, it's 12 N2. Another one that's really easy in this case would be chlorine. So you're going to go to HCl. You're going to have 24 HCl. The reason that chlorine is so straightforward here is because we have a fuel and an oxidizer. If we had multiple fuels, like let's say we introduce a metal into here, we're going to start to get potential chloride products, and it gets really confusing. It makes it impossible to predict what the reaction pathway is going to be. When you only have a fuel and an oxidizer, it makes things pretty simple, even when you introduce metals. So because this is the first example that we're talking about, that's why we're keeping it simple with two components, a fuel and an oxidizer. It keeps things simple, and all the chlorine is just going to go to HCl. Your total number of carbons is 30 that you tallied up. That's going to go to 30 CO2. It's really straightforward. What hydrogen is going to go to is H2O. So H2O, if you'll notice, that's H2. That means that it's 2 hydrogens. So you take your total number of remaining hydrogens, 132, divided by 2, because it's going to go into H2O, and that's going to give you 66. Now we go into the remainder, which is going to be oxygen, right? So the total number of oxygen that we had, if you'll recall, was 126 oxygen. We already figured out other reactant products that'll have oxygen, so we figured out CO2. So what we can do is we can take 126 total oxygens, and we can remove how many oxygens were in the total number of CO2. So we had 30 CO2 was what we already figured out from an earlier product for carbon, right? So we take 126 oxygen minus 30 oxygen times 2, because it's CO2, right? CO2, so that's 2 oxygens. So you double it, right? So that's 60 oxygen. So we go the total of 126 oxygens that are available minus 60 gives us 66. And we already figured out that, H2O from when we figured out hydrogen is 66. So this all lines up. Let's just spell it out here. So we're reacting 24 units of ammonium perchlorate, 5 units of glucose, and it's going to give us a product or detonation product of 12 dinitrogens, 24 HCl's, 66 H2Os, and 30 CO2s. That's our products. So this is something that can be done for any fuel and oxidizer that is going to be used in an energetic composition. You should balance out. It's not always necessary. There's in fact some shortcuts that I use that we'll get into when we get into multi-component mixtures, where we don't actually have to use balancing of an equation. But the meat and potatoes of coming up with an energetic design in terms of advanced explosive design is balancing a fuel and an oxidizer. Now, why that's important is that if you, if you had a different number of reaction products that were, a different number of nitrogens versus your input nitrogens or oxygens or whatever, that means you messed up something and your ratios are wrong. So when you go to do your ratios for weight to actually, make the physical mixture of the composition, you're going to be incorrect, and you're not going to get maximum detonation potential, maximum energy release from the explosive composition, and that is why it's necessary to balance equations. Okay, so the reason that I'm wearing a hood is because I keep having to run outside and it's snowing a lot. I have to go out to get more beer. I'm enjoying the refreshments. It's actually not a part of pyrovalence calculations, so you don't need to do that. It just helps me with math. On that first example that we gave, ammonium perchlorate and glucose, we were just taking baby steps. Now let's get into a system that people would actually it's a practical thing that people would want to know. So ammonium nitrate, nitromethane, that would be known as ANNM is what it's commonly known as. So this is, a nitroparaffin, that's nitromethane. It's an explosive. It's a fuel. I'll tell you that up front. And you're mixing it with ammonium nitrate as an oxidizer in order to maximize the potential detonation of the nitromethane. The result of this is that, nitromethane itself, if you try to detonate nitromethane, it's actually extremely insensitive. When you mix in ammonium nitrate, it becomes quite sensitized. So it's much more sensitized than straight nitromethane. So this is always a consideration when you're developing an explosive composition, is handling properties, sensitivity. You always want to keep this in mind before you jump into something. Okay, so we want to mix ammonium nitrate and nitromethane. The very first thing that I'm going to do is go to Wikipedia. I'm going to pull up both ammonium nitrate and nitromethane. Scroll down to the right side. It's going to have the molar weights of these molecules. So for ammonium nitrate, the molar weight is going to be 80.043. That's the number. It's grams per moles. Grams per moles doesn't really matter. What's important is that you get that molar weight of the molecule. So 80.043 is what you need to remember. After you do this enough, common oxidizers, ammonium nitrate, ammonium perchlorate, you're gonna memorize all of this stuff. You won't need to look it up. Nitromethane is a little less common, so that is 61.04 grams per moles. You'll want to use this. The reason that we're getting the mole weights is because this is what we're going to use when we go from the balanced equation into actually, like writing out our ratios of weight for what we want to mix together physically. The next thing that we need to do is figure out the pyrovalence of each of them. So we're going to add up, nitrogen, hydrogen, nitrogen, oxygen for the ammonium nitrate, and carbon, hydrogen, nitrogen, and oxygen numbers for the nitromethane, and that's going to give us a total for each of them. We're going to get -2 for ammonium nitrate, that is an oxidizer, and we're going to get +3 on the pyrovalence for nitromethane because it is a fuel. -2 and +3. That is what we're going to input into our balanced equation. So between these two numbers, the -2 and the +3, we would want to find the lowest factors. 2 and 3 are already at the lowest factor. Now we're going to plug in the left side of our equation. That's the reactant side of the equation. So what do? Well, we take that -2 from the ammonium nitrate and we're going to put that on the fuel. And we're going to take the +3 from the nitromethane and we're going to put the 3 on ammonium nitrate. So it's the left side of the equation is 3 ammonium nitrates and 2 nitromethanes. So that's 3 NH4NO3 plus 2 CH3NO2. Now, in terms of balancing the equation, this one's pretty simple and straightforward. So now that you have your total layout of each of the individual elements, what exists on the left side of the equation, now you go into common reaction products, what you should expect. I like to go left to right, just like on the left side of the equation here. I do the same thing in the same order on the right side. So the first thing I'm going to have is nitrogen because that's the first element on the left side. So I'm going to have 4 N2s, I'm going to have 9 H2Os, and I'm going to have 2 CO2s. So it's a pretty basic and simple reaction here. And from this balanced equation, now we can convert into actual units, and this is what we would do in a real-life advanced explosive composition design. When you're coming up with these pyrovalence numbers, what you're doing is connecting the detonation product pyrovalence to a mole of the material, right? Well, when you did this balanced equation, 3 ammonium nitrates and 2 nitromethanes, the 3 and the 2, it can be interchanged with mole. So these are just units, A mil is a mil and a mole is a mole. So you got 3 ammonium nitrates and you got 2 nitromethanes. Now we want to convert them into weights, right? Because we're actually going to measure out these materials. We're going to measure out an amount of ammonium nitrate, and we're going to measure out an amount of nitromethane, and we're going to mix them together. And that's how we're going to get maximum optimized detonation energy out of this explosive composition. So the way we do that is we just replace, now that we've balanced everything and we know that everything is correct, now we replace each material with the molar weight. Ammonium nitrate, the molar weight, this is why you went and got that from Wikipedia in the first place, 80.043. So 3 ammonium nitrates, 2 nitromethanes, that means 3 80.043, the molecular weight of ammonium nitrate, and 2 61.04, which is the molecular weight of nitromethane. Now we are still adding those together because nothing changes. You're just inserting the molecular weight in place of the molecular composition. So the result of that, if you do 3 times 80.043, the result is 240.129. And from 2 times 61.04, you're going to get 122.08. When you solve those, when you get that 240.129 and 122.08, you add those together just like the left side of the equation, and that's going to give you a total of 362.20. So that is the total molecular weight of this composition. You now have to go into separating the two to know which one, how much fuel and how much oxidizer. This is cross multiplication. So the way this works is 2 fractions that you're assigning 362.2. That's the total of adding together these molecular weights times the correct balanced valence states. That's where you're getting 362.20. That is equivalent to 100%. So that is 100% of your composition. Okay. What you need to figure out is what each element is of that composition. So your total of ammonium nitrate is 240.129. So what that means is that you're going to write out cross multiplication 100 times 240.19, and then you divide the result of that by the total 362.2, and that's going to give you 66.26. That number is the percentage of ammonium nitrate that you would use in a balanced composition with nitromethane. You can, if you want, you can then go through and figure out your nitromethane. So that would be 100 times 122.08 divided by 362.2 is going to give you 33.70%. So the end result in terms of percentage ratios, how you would calculate weight for a composition of ammonium nitrate and nitromethane, you're going to have 66.26% of ammonium nitrate and 33.70% of nitromethane. That's actually, I see a calculation error here. It's very minor. It's within insignificant margins of the significant figures, so it doesn't really matter. What I would do in this case is round it to 66 and 34. So 66 ammonium nitrate, 34 nitromethane. If you go into the Science Madness, their page on AN, NNM, ammonium nitrate, nitromethane, they're going to recommend a ratio of 60-40, which is actually fuel rich, technically. So they probably, whoever came up with that, probably derived that from experimental testing. There may be validity to their experimental testing. It may have some kind of unforeseen reaction pathway that actually, gives the most energy at a ratio of 60-40. But in terms of theoretical, technical, calculating out, what is going to be optimum detonation energy out of ammonium nitrate and nitromethane, the ratio is going to be 66-34, and that's probably higher energy than 60-40. Okay, we are on the last drink here, so hopefully we can finish this up. Hopefully. So let's get into a common system that people would want to do, and it lets us kind of contrast theory to actual, ammonium nitrate to fuel oil. That is known as ANFO. ANFO is extremely common. It's extremely practical. It's a boring explosive. It's a heaving explosive. They use that in quarrying. It's very popular. So this is what I'm going to do. It's the same as before. I'm going to take ammonium nitrate. I'm going to look up the molar weight of it, 80.043. I'm going to look up for a fuel oil, common fuel oil, a common, it's a repeating unit normally. So it's CH2 would be a common, molecular, the molecular layout of fuel oil. So CH2 is going to have a mole weight of 14. So now I have my molar weights for both ammonium nitrate and fuel oil. I'm going to find their pyrovalences. Therefore, ammonium nitrate is -2, an oxidizer. For the hydrocarbon unit, CH2, the total, adding those together, is +6. That's a fuel, right? Fuel oil. So now I have both my molecular weights and my pyrovalences of each reactant that's going to be used here in this detonation. And in terms of the pyrovalences, we are dealing with -2 and +6. So we're going to factor, right? That's the next step. We're going to factor those two numbers. So we're going to get 1 and 3. So from the basic equation, we're going to replace each molecule with the mole weight. So for ammonium nitrate, 80.043. And for the hydrocarbon there, the fuel oil, 14, right? Those are the molecular weights. So we have 3 times 80.043 plus 1 times 14. We just simply plug in the math. So 3 times 80.043, that's going to be 240.129. The fuel oil, 1 times 14, obviously that's 14. And so you get 240.129 plus 14 is going to give you a total of 254.129. That is 100% of your composition, and now you have to figure out each element of reducer and oxidizer. So the first thing that I do is oxidizer. So I'm going to take 100 times 240.129, and I'm going to divide that by the total, 254.129. That's going to give me a 94.49 answer. Ammonium nitrate percentage is going to be 94.49. Then I'm going to go 100 times 14. The 14 comes from the fuel oil molecular weight because we only have one of them. So 100 times 14 divided by 254.129 is going to be 5.509. That's a percentage. That's going to be the fuel oil. And so when you get down to the ratios here, you're going to be 94.49% ammonium nitrate and 5.5% fuel. 94.5 to 5.5. Interestingly enough, if we go to Wikipedia's page for ANFO, they have their own ratio that they listed on there. It's going to be 94 and 6. So it's technically, you're actually getting a little bit fuel rich here, but they rounded it, right? So this is what you're going to find that's common across all domains. So when you go into patents for novel explosives that people have developed, whatever, if they've done a lot of testing, it's going to end up being through their trial and error, blood, sweat, and tears, you're going to find the result of exactly what you're going to get from instituting the pyrovalent system. So pyrovalent system is absolutely a game changer. It's what you need to use and understand. It's what you need to memorize in order to be a highly efficient sapper and do advanced explosive designs. Now, I don't want to insult you. I don't think we need to go into, how to take that ratio and apply it to weight, but just in case anybody's, straddling behind here, we want to catch everybody up. So, for example, if we want ANFO, you usually use ANFO in larger charges. That's what makes sense. So, if we take ANFO, let's say like 1 kilogram of ANFO, right? 1 kilogram, that's 1,000 grams. This is why you use the metric system anytime that you're dealing with, explosives. You'll want to use SI. You're going to use metric system. So 1,000 gram ANFO charge, that's what you want. That's your goal, right? So you take it and you take that percentage, 94.49, that turns into 0.949. And that's going to give you 949 grams of ammonium nitrate. And then, in terms of your fuel oil, you would take 1,000 grams because it's only 5.5%. You're going to go 0.055 times, right? And that's going to give you 55 grams of your fuel oil. And now you know the weights, the exact weights that you weigh out on a scale, and you mix them together, and now you have your optimized highest performance detonation ammo composition that you can possibly get.